for moving forward, a lot of what we're going to be doing in what the skill you need to develop is look at a starting material, identify the major functional groups, diagnose the conditions, and then be able to predict the product. So that's a skill of this class. So sodium ethoxide is our base for the E2 reaction. Notice that this conjugate base is associated with this acid, right? So we're using this acid, which is the solvent. This base is actually generated directly from ethanol. You pour your ethanol into a flask. Ethanol is a clear, colorless liquid. It has a sort of a sweet smell to it. It is the active ingredient in most alcohol that you end up consuming. So you take ethanol and then you basically add elemental sodium to it in little chunks. You'll then see some fizzing, and the sodium metal dissolves. It goes into solution, and it generates the sodium ethoxide. So again, moving forward, you want to know what these things do. So if this is acting as a base, it's going to do an elimination. And so if it eliminates the hydrogen that I've shown in the plane, that's anti-periplanar to the bromide, what is the name of the product that's formed? You write that in the chat. My eyes will see it. That information will throw out to my arm, and I'll write it down on the screen. So write the name of the product that's formed, and I'll draw the structure on the screen. So Mac and Aiden are pretty quick. Mac drew it in sort of the condensed line formula as best you can with the keyboard. So trans 2-butene, again, that's the correct answer here. So trans, because this methyl group is going to be on opposite face of the pi bond than this one. So we'll write and again, the major product is trans because when we look at the Newman projection, that places the methyl groups 180 degrees from one another. So what are the other things that are formed? Sodium bromide. That's your inorganic byproduct, and then the ethanol is also produced after the abstraction. So here's the E1. The E1 substrate. Now we have a tertiary alcohol. We're doing E1. So for example, we would treat this, say, in the presence of sulfuric acid and heat. So it's doing an elimination. So what is the product? What is the name of the product from this reaction? So you're starting with a tertiary alcohol. You're treating with sulfuric acid and heat. It's going to do an E1 elimination. So Aiden says 2-methyl-2-butene. Cole follows up with 2-methyl-2-butene. So here we have 2-methyl-2-butene. So let me, I don't want you guys to forget all the stuff we've talked about. So 2-methyl-2-butene. How many unique carbons do you see in 2-methyl-2-butene? So I see a lot of 4s. I see a 5. Let me put something in here. I'm gonna put in the hydrogen on the alkene. So when I do that, does that sway your answer any? Again, we're talking about unique carbons. I'm putting that H in there for a specific reason. So Blakely, maybe think about this as, you remember that movie Speed with Keanu Reeves? You got to cut one wire, the red or the blue. Which one are you going to cut? So pick an answer, 4 or 5. Can't be both. So 5, Aislinn says, I think 5. I'm going to say 5 as well is probably the best answer. And the reason I put this H in is because when you look at this molecule, you have methyl, methyl, methyl. Those methyls are all different because of their relationship to this hydrogen. Even though this sp2 hybridized carbon has 2 methyls, so this sp2 hybridized carbon has methyl group, methyl group. This methyl group is on the same face as this H. This one is opposite, so these cannot be the same. This also cannot be the same because it's bonded to its own sp2 hybridized carbon, and it has a different relationship to that H. So again, you can a way to think about this, if you shrunk yourself down to nanometer or angstrom scale, and you were standing here and you were walking this path, is this path the same as this path? So if you visually can't see it, think about yourself standing there walking these different paths. So let's go ahead and count them. 1, 2, 3, 4, 5. So let me further ask you, so sp3 hybridized carbons are 1, 3, and 5. sp2 hybridized carbons are 2 and 4. Where do you expect to see the chemical shift of 1, 3, and 5? Where do you expect to see the chemical shift of 2 and 4? So I'm looking for specific number ranges. So remember that the C13 spectrum is 220 parts per million on the left, 0 parts per million on the right. The location of the carbon hybridization indicates its functional group. So what range do you expect to see carbons 1, 3, and 5 versus carbons 2 and 4? Does anyone remember? So Cole and Aiden say for sp3 between 0 and 50. Yeah, I would say we're going to push a little bit further away from a normal sp2 or sp3 hybridized, just because these are allylic, and that sort of shifts it more to the left. So let's say 20 to 40 or something, 20 to 50. So I'll write 20 to 50. Again, this is ppm. That's the chemical shift. So what about sp2 of the double bond? Where do those occur? So Cole says 100 to 150. Yeah, I'm going to just trim that back a little bit and say most typically, say like 120 to 140. Sort of when you get, if your range is too large, you start encompassing other things. So around 100 is maybe SP. So I'm going to say 120 to say 140. So what about the proton? How many unique sets of protons do you see for this molecule? 2-methyl-2-butene. So unique sets, how many total, and then the ratios. So 4 is a good answer. So I'm gonna renumber these in blue. So 1, 2, 3, 4. And then Aiden says 3 to 3 to 3 to 1. So methyl to methyl to methyl to the vinyl. So 3 to 3 to 3 to 1. So again, I encourage you to think about how would you describe any sort of product from a reaction spectroscopy, using spectroscopy as a review so you don't forget all the stuff that you learned. So let's move on to our first addition reaction of an alkene, and maybe what we'll do is just use the trans-2-butene from above. So there's our trans-2-butene. So we're going to treat that with 1 equivalent of hydrogen gas and say we're going to run this reaction with palladium metal, PD. And then I'm going to use this nomenclature /C. What that means is the palladium metal is adsorbed onto charcoal. So C is carbon or charcoal. Just like if you grill something and you have like a charcoal briquette and you touch it and you get that like dust on your fingers, that's what this looks like. It's just like a black powder that has palladium adsorbed on it. The palladium metal is a catalyst that helps split up the hydrogen, H2, and then add it to the alkene. So we typically run these in a solvent that's alcoholic, say methanol. So what we're going to do is then add H2 across that alkene. So each carbon of the sp2 hybridized double bond becomes sp3 hybridized, and it gets a hydrogen. So what do we end up with? So we change hybridization through the process, and overall this is an addition of an electrophile to the pi bond. So the pi bond is your nucleophile that's supplying the electrons to bond to those hydrogen atoms in hydrogen gas. So when we talked about degrees of unsaturation, this is what we were talking about, how we determine that experimentally, because you can measure the amount of hydrogen gas that's taken up in this process. So any questions so far? So all I'm saying is that this coefficient is 1 because there's one double bond. So I want to introduce a new term now called regiochemistry. And I'm going to use a very general scenario to describe this. So every reaction that we're going to learn for this chapter, this module, is called an addition reaction. We're adding something to the alkene, and as we'll see when I write it down and we start numbering some things, the electrophile can add in different ways, and that word is called regiochemistry. So let's consider this is just a general alkene. I'm showing you that double bond. I haven't specified substituents. I just put bonds off of them. Then I'm calling the carbon on the left carbon 1, the carbon on the right carbon 2, just to track. All I'm doing, we're just doing that to track. The pi bond is the nucleophile. It's supplying the electrons. A nucleophile always reacts with an electrophile. So I want to designate, for now, the electrophilic reagent is AB. In one mode of addition, carbon 1 gets A, carbon 2 gets B. So I'm not showing you how the arrows are pushed or anything just yet. I'm just telling you overall this is what's happening. A adds to C1, B adds to C2. So that's one way that reagent, whatever it is, AB, can add to the alkene. But you could also ask the question, can B add to C1 and A add to C2? Yes, that is the alternative thing that can happen. So that would sort of be oriented like this then. Getting ahead of myself here. This should be A. So this is, again, the progression of difficulty in this course, because you have to diagnose what the starting alkene is, what these reagents are, and which mode of addition is going to be preferred. That word is called regiochemistry. You have a decision to make. And if you've really been putting the effort into this class, we're going to rely on all the fundamental stuff we've been talking about. But I'm telling you, this is a point that students can find difficult, because if you're just simply out to memorize things, this is where the memorization is going to fail you, because you really have to put thought into why one pathway is preferred over the other. So does everyone just understand the generality of what I just drew up there? So now I'm going to further complicate this. Other contributing factors. So if you pay attention to the news and COVID, you know, they talk about why people end up in the hospital and pass away from COVID. They say there's these other contributing factors or comorbidities. So these are things that complicate the process. What are other contributing factors? The starting geometry of your alkene, whether it's E or Z, that contributes to the outcome. And the facial selectivity of the addition, for lack of a better word for describing this now, I'm just saying top or bottom. So maybe let me just point that out real quick, and we'll see it in the mechanisms as we go through. So E and Z, so for example, we saw the trans, this is the E, trans 2-butene. This is the cis. So those are examples of that. What do I mean by facial selectivity? So let me use the trans as an example. So we have, there's sort of the trans 2-butene, where this methyl and this hydrogen, now we're viewing it where those are coming out towards you, and then these are projected away from you. So what do I mean by top facial selectivity? So that would sort of be the electrophile approaching from the top face. This would be the electrophile approaching from the bottom face. And that's complicated by the fact that, you know, it doesn't have to be AB, it can be BA, just as we talked about up here. So not only do you have to worry about that regiochemical issue, you have to worry about, is it approaching this way or from the bottom? So there's a lot of mechanistic thought that goes into understanding these addition reactions. Any questions on this slide so far? What we're then going to transition to on the next slide is I'm going to give you a summary table of these reactions, and then we're going to go into depth of each one. So what I'm going to do is just summarize these different reactions according to this format. The alkene, what type of addition it is, and then what elements are added to the alkene. Now, this is not meant to be the specific reagents that we're using. It's just showing you the elements that add. So we're just being really general here for now. So number one, the type is hydrogenation. So we're gonna assume this is the starting material. The type, hydrogenation, here's our arrow. The elements, the product that we end up with. So the product, which I'm going to draw here, we're taking the alkene and we're making an alkane. So alkene to alkane occurs through hydrogenation, and we're adding H to each sp2 hybridized carbon. Our number two reaction is called hydration. We're going to add an H to one carbon and an OH to the other. So now you can see the difference of A versus B in that general electrophile. So H, OH. So you see these elements, H, OH. Is everyone sort of clear now on this could be A versus B? So if you think about the starting alkene, you're starting with, is it mono substituted, di, tri, tetra substituted? You have to decide which carbon gets the H, and then as a consequence of that, which gets the OH. Our third reaction type is called hydrohalogenation. So hydrohalogenation, we're going to add the elements of HX, where X is equal to chlorine, bromine, or iodine. HF is not a good substrate for this. So we're converting an alkene to an alkyl halide. Our next reaction is hydroboration oxidation. So again, I'm showing this very general. So this is a two-step process, hydroboration. So the first thing we're adding is hydrogen, and then this boron group. That is typically not isolated. We add a second set of reagents that do an oxidation, where the boron is transformed into an alcohol, so OH. So compare this alcohol to this alcohol. I have an existing video screencast that's already posted that you should probably watch that compares hydration versus hydroboration, in that when you run this versus that, you end up with different regioisomers of those alcohols. That's where the word regiochemistry really comes into play. It's a good example. Our fifth one is called halogenation. We're adding molecular halogens. And did you guys run this reaction this semester where you took an alkene, you added, say, bromine water, bromine itself, and then you saw as you dripped in like the brown bromine, it decolorized as it added, and then you got to a point where the color was maintained in the solution. So yeah, that's this reaction here. But none of our groups yielded any results. That's life. I know as undergraduate students, you want to go into lab, and everything you do is perfect, and you get this nice answer, but that's not how the world works. And you will find that the stuff you read in these textbooks is very sterilized. The information has been filtered, in that when you actually get into the real world and do it, it's messy, it's not clean. And so the sooner you sort of accept that, the more you can move on and I don't know, grow as a student, I guess. So look at conditions 3, hydrohalogenation. We're only putting on one halogen, whereas in these, we're putting on two halogenations that are next door to one another. So we end up with different functional groups there. We end up with a dihalide. So condition 6 are what has been mentioned in the chat already, Halohydrin. So these are slightly different than 5. So this would have been like the bromine water. So you're ending up with, so there's the halo, this part is the hydrin, it's an alcohol. So it's a 1-2 relationship between an alkyl halide and an alcohol. So the difference between conditions 5 and 6 is that you run 6 with a protic solvent, 5 you do not. Condition 7, this is called dihydroxylation. So we're adding these elements across the alkene. So we now end up with a 1,2 diol. And then finally, the type is oxidative cleavage. We're adding oxygen across the alkene. Where you're converting the carbon-carbon double bond into carbon-oxygen double bonds. So that's called oxidative cleavage, and then we're going to learn the reagents to do that. So that's what we're going to do over the next couple lectures, is look at the reagents and the mechanisms by how these things happen. So before I move on from this summary slide, are there any questions? Maybe let me just point out, again as a refresher, how would you know that these things happened spectroscopy-wise? Again, you would see different carbon shifts from an alkene forming an alcohol. You have your OH and the IR. Your alkyl halide, remember the mass spec. Chlorine has a 3-to-1 ratio of the parent. Bromine has 1-to-1 ratio. Iodine, you see a signal at 127, which corresponds to the iodide anion. Alcohol again, IR. Halogenation, now you have 2 of those, so the parent regions would look a little bit more complicated because now you're considering 2 halogens. Here you have OH and the IR and the halogen and the mass spec. Again, IR for OHs. Now for oxidative cleavage, you're going to see the carbonyl stretch in the 16 to 1800 region. So again, those are methods of spectroscopy you can use to determine the product formation. So I'm going to start with alkene hydration, and then this is the synthesis of alcohols from alkenes. And as we'll see with the concept of microscopic reversibility, we're taking an alkene, making an alcohol, and we saw on the introduction slide we can take an alcohol to make an alkene. Really the difference is the concentration of the reagents that you use. So here's a reaction, and let's consider it. So we're running the reaction of 2-methylpropene in dilute, very dilute sulfuric acid. The bracket of the square bracket of sulfuric acid means it's a catalyst. What we mean by that is we're lowering the energy of activation in the mechanism, but also the catalyst molecules, the elements in that catalyst are not incorporated into the product. So when we do this alkene hydration, we end up with this. What's the classification of this alcohol? So I've shown you the elements of water, that's the hydration, adding to the alkene. So this is tertiary. What about the other alcohol here? What's the classification of this alcohol? This is primary. Under these conditions, you only form the tertiary and not the primary. Now, if we're thinking mechanistically about what an addition reaction is, We've said that the alkene is the nucleophile. The nucleophile supplies the electrons. This forms H3O plus, right? Because water is a leveling solvent. Any strong acid is leveled to hydronium, which is H3O plus. This is the nucleophile. This is the electrophile. What is the first step in the mechanism of converting this alkene to either of these alcohols? Now that's the choice you have to make. Why is this preferred and not this? What's the first step we need to do? So I'm saying this is a nucleophile, this is an electrophile. Alternatively, H3O plus is an acid, this has to be a base. If this is a base abstracting a proton, you have two choices. I've numbered carbons 1 and 2. Explain to me the reason why that carbon 1, why does carbon 1 get the hydrogen? So Blakely, think a little bit deeper mechanistically about what happens after carbon 1 is protonated versus protonating carbon 2. So this is what I meant by regiochemistry. In this bottom path here, I'm saying C1 gets the H. So that's an acid base or a proton transfer. Now what is left here after I do that? What's left at that position? So carbocation is probably the preferred word for what Blakely wrote in her response. What is the classification of that carbocation? Max says tertiary. And now I cannot stress this enough to you. I know that as a student, you want to know the right answer, and maybe that's all you want to know. But when you are deciding something, you have to look at all possible routes to get to that answer. Now let's evaluate if carbon 2 gets the proton, what that structure is, and then we have to compare. When that happens, That's what we get. And what is the classification of that carbocation? Blakely says primary. So as a reminder, which one of these carbocations is the most stable? The tertiary is. So Hannah, to answer your question, this route will not form because you can automatically form this tertiary carbocation. So you're not going to go this way and have it rearrange because you can automatically go this way. So let me just graph this as a refresher of chapter 6. So here's our theoretically speaking, if it did happen, it would rearrange. So here's our reaction coordinate. Again, time is progressing to the right. Free energy on this scale, and again, it's all relative. So all I'm doing is I'm graphing this now. So here's your starting material. It's at some energy. As the reaction proceeds, the tertiary carbocation is lower in energy than the primary. So when we think about this mechanistic drawing here, these arrows, this should also be in your mind concurrently. When we're saying that the tertiary is lower in energy, both of these are higher in energy than the starting material, again, because the carbon's electron deficient and it wants to react. That's what we mean. When we're comparing them, we say the tertiary is more stabilized than the primary. We're saying that the starting material doesn't have to go up as high in energy as it does for the primary. So that's really what we're getting at. So this then moves on. We now have nucleophile water attracted to the electrophile carbocation. We've now added the O8, the oxygen to that carbon. We're now doing a proton transfer. So an acid-base reaction. To end up with our final neutral product. So this is the thought process that we need to deploy when we're thinking about these addition reactions. So this specific mechanism deals with regiochemistry. That's this point right here. That's regiochemistry. That's what we mean by that. which carbon atom is getting the first element of the electrophile. As we learn more of these different conditions, that's when it gets complicated and the EZ comes into play, and then the facial selectivity also comes into play. So given the